Hello and welcome in this new video. In this video, we're going to see the solution of question 7 of assignment 3rd in data science. The question number 7 says differentiate the logistic regression and linear regression on the basis of hypothesis, parameter and cost function. How the gradient descent algorithm is used to optimize the parameters. We start with the linear versus logistic regression, a deep dive. Understanding the fundamentals of concept and differentiating between two powerful predictive models in machine learning. Hypothesis, parameters, cost, and optimization. Hypothesis is defining the underlying assumption and output type of each model. Parameters, exploring the coefficient and incept learning from the data. Cost function, quantifying the error and guiding the model improvement. And the optimization, utilize the gradient descent to find optimal parameter values. Linear regression on the basis of hypothesis goal. The hypothesis given in this chart, linear regression assumption as a linear relationship between the input feature x and the continuous output variable x. It models the relationship and straight line equals to this formula y equals to beta 0 plus beta 1 x1 plus so on and to the beta n nxn. Goal to find the best fitting straight line that minimize the solution of square difference between the predicted and actual output values. This line is used for making predictions on new and unseen data, predicting the continuous values like horse price and temperature. Understanding the strength and direction of the relationship between the variables. The logistic regression embraces the probability hypothesis and their goal. Logistic model that probability that an input belong to a certain class. It uses the sigmoid logistic function to map any real value number into a probability between 0 and 1. The formula of this is given in this table, and the graph shows the actual logistic regression by the plotting values of this. And goal to find the parameters beta values that best separate the class and allowing the prediction of categorical outcomes, e.g., yes, no, spamming, and not spamming. Classify the data points into two or more discrete categories. Estimate the likelihood of an event occurring. In key parameters, what we the learn from data, coefficient beta 1 to beta n. This determines the strength and direction of the relationship between each independent variable and the dependent variable. Linear regression directly impact the predicted continuous value, and logistic regression impact the long odds of the outcome, influencing the probability. In intercept beta 0, this is a predicted value that depends variables when all independent variables are 0. Linear regression, the point where the regression line crosses the y-axis, and logistic regression influence the baseline probability when no feature are present. The cost function measure error in the linear regression according to this graph. Mean square error, called MSE, the most common cost function of linear regression. It calculates the average of the squares difference between the predicted value y bar and actual value of y. By the formula of this, squaring errors penalizes larger error more heavily, and minimizing MSE aim to find the lean line that is close to the all data points. The cost function maximizing likelihood in the logistic regression. Long loss cross entropy. Logistic regression use long loss, which is designed to penalize incorrect classification. It measures the performance of classification model whose output is probably between the 0 and 1 by the formula of long loss. penalize the high confidence in an incorrect prediction, encourage the model to predict the probabilities to close to 0 for the class 0 and close to 1 for class 1. Coordinate descents. The path to optimize. Start with the random parameters, begin with the arbitrary initial value for the model's parameter, beta 0, comma beta 1, etc. Calculate the quadrants and determining the partial deviations of the cost function with respect to each parameters. This indicates the direction of the step best ascents. Take a step down, update the parameters by subtracting the learning rates, multiply by the gradients. This moves the parameters in the direction of reduce the cost. Repeat until convergence. Iterate the process until the change in the cost function become very small, indicating that a local or a global minimum has been reached. Visualizing quadrants descent, finding the minimum. Imagine a cost function as a landscape with the hills and valleys. You can see in this graph, in this image. Gradients descendant is like a hiker trying to find the lowest point in valley. The minimum cost learning rate, the size of each step the hiker takes. A small step takes longer but is lessly likely to overshoot. A large step is faster but might miss the minimum. Local versus global minimum. Gradient descent can something get stuck in the local minimum if the landscape has many dips. Different starting points or advanced technology can help find the global minimum. In both linear and logistic regression, gradients descendant systematically adjust the beta parameters to minimize their respective and cost functions. Thank you.